Hello dear students, in this video I'll continue with revision for CBSE board exam, and in this video I'll solve the questions from exercises of chapter 2 Algebra from the CBSE Handbook. So here we have the first exercise. The first question: identify the type of matrices given below and write the order of each matrix. The first one is A equal to 2, 3. So here we can see that this matrix A has got only one row. So it is a row matrix and it has 1 rows and 2 columns. The order is 1 by 2. Next we have the matrix B. It has got only 1 column for given number of rows. So it is a column matrix. And the order of the matrix is it has 3 rows and 1 column. So order is 3 by 1. Next we have the next matrix C. Here we can see that the number of rows are not equal to the number of columns. So it is a rectangular matrix. And the order is it has got 3 rows and 2 columns. So the order is 3 by 2. Next we have the next matrix D equal to this matrix 1, 3, minus 4. Again it has got only 1 row. So it is a row matrix for given number of columns. So it has 1 row and 3 columns. The order is 1 by 3. The next question is this matrix has got equal number of rows and columns. So it is a square matrix. And this matrix it has got 2 rows and 2 columns. So the order is 2 by 2. The next matrix again has equal number of rows and columns. So it is a square matrix and the order is it has got 3 rows and 3 columns. Order is 3 by 3. And then the next matrix, it has all entries 0. So it is a 0 matrix with 2 rows and 2 columns. So the order is 2 by 2. Again this is also a 0 matrix. R equal to, it has got 2 rows and 3 columns. So the order is 2 by 3. And next we have the next matrix X given by 1, 0, 0, 0, 1, 0, 0, 0, 1. Here this is an identity matrix. Here the elements in the diagonal are all equal to 1. So such a matrix is called identity matrix. And the order is it has got 3 rows and 3 columns. So the order is either 3 or we can write it as 3 by 3. And the next matrix is this matrix, that is equal to 2, 0, 0, 0, 2, 0, 0, 0, 2. Here we can see that the diagonal elements are equal. If the diagonal elements are same, then and it is a square matrix, when all the other entries are 0, then such a matrix is called a scalar matrix. So this is a scalar matrix of order 3 by 3. Let us continue. The next question. Given this is the matrix A, we have to write the element A12. A12 is the element in the first row and the second column. So this is A12. So A12 equal to minus 4. Next question. B equal to this given matrix. Find the sum of the elements at B22 and B32. Now B22 is the element in the second row and the second column. This is 0. And B32, it is the element in the third row and the second column. It is 2. So B22 plus B32, it is 0 plus 2, which is equal to 2. Next we have C as this given matrix. Find C21 plus C32 minus C13. So here C21 is the element in the second row and the first column, it is minus 1. Then C32 is the element in the third row and the second column, it is 2. And C13 is the element in the first row and the third column, it is minus 3. So C21 plus C32 minus C13, it is minus 1 plus 2 minus of minus 3, which is plus 3. So it is 5 minus 1 equal to 4. Next question. Construct matrix A equal to matrix Aij of order 2 by 3 where Aij equal to I plus 2j the whole square by 2. So here we have to construct a matrix Aij of order 2 by 3. So first let us write a matrix of order 2 by 3 in the general form. It has 2 rows and 3 columns. So matrix A can be given by, let A equal to A11, A12, A13, A21, A22, A23. So here Aij is given by I plus 2j the whole square by 2. So A11 will be 1 plus 2 the whole square by 2. It is 9 by 2. Then A12 will be 1 plus 4 the whole square by 2. It is 5 square by 2, 25 by 2. Then A13 will be 1 plus 6 the whole square by 2. It is 7 square by 2, which is 49 by 2. Then A21 will be 2 plus 2 the whole square by 2. It is 4 square, which is 16 by 2, 8. Then A22 will be 2 plus 4 the whole square by 2. It is 6 square by 2, which is 36 by 2, 18. Then A23 will be 2 plus 6 the whole square by 2. It is 8 square by 2, which is 64 by 2, 32. So the matrix A is 9 by 2, 25 by 2, 49 by 2, 8, 18 and 32. So this is matrix A. Next question. Construct matrix B equal to Bij of order 2 by 2 where Bij equal to mod I minus j by 3. So we have to find the absolute value of I minus j for each element divided by 3. So let us take let B equal to B11. It is a matrix of order 2 by 2. So it has 2 rows and 2 columns. B22. So B11 will be mod 1 minus 1 by 3. It is 0 by 3, 0. Then B12 will be mod 1 minus 2 by 3. It is mod minus 1, which is 1. So it is 1 by 3. Then B21 will be mod 2 minus 1 by 3. It is 1 by 3. Then mod B22 will be mod 2 minus 2 by 3. It is 0. So this is 0, 1 by 3, 1 by 3, 0. So this is the matrix B. Next question. How many distinct 2 by 2 matrices can be formed by using numbers 5, 7, minus 1? Justify your answer. So here we have to find the number of distinct 2 by 2 matrices which can be formed using these 3 numbers. So if we consider a 2 by 2 matrix, say A, then a 2 by 2 matrix, it can have these 4 elements. Now each of these elements, it can be filled using these 3 ways. The first element can be filled using one of these 3 ways, 5, 7, minus 1. Then the second element in one of these 3 ways, the third element in one of these 3 ways, and the fourth element in one of these 3 ways. So the total number of ways will be 3 into 3 into 3 into 3, which is 3 raised to 4 by fundamental principle of counting. So here a 2 by 2 matrix has 4 elements. Each element can be filled in 3 ways. So by fundamental principle of counting, the required number of distinct 2 by 2 matrices, it is equal to 3 raised to 4, which is 81 ways. Matrices that can be formed. Next question. A matrix has 14 elements. How many matrices of different orders are possible? So if we have a matrix of order m by n, it means the number of elements in this matrix is m into n. So if a matrix has got these 14 elements, then the number of possible different orders are the number of ordered pairs which are obtained by the factors of 14. So in a matrix of order m by n, we have mn number of elements. So this 14, it can be written as 1 into 14 or 14 into 1 or 7 into 2 or 2 into 7. Hence, this matrix can have possible orders 1 by 14, 14 by 1, 7 by 2 and 2 by 7. So these are the different possible orders for a matrix which has 14 elements. Next question, find the values of A, B, C and D from the equation. So here we have these two matrices equal. So we can compare these two, each of these elements, and we can find the values of A, B, C and D. Comparing. So here we can see that A equal to 14. A equal to 14. Then A plus B equal to minus B implies 2B equal to minus A. A we got it as 14. So this is equal to minus 14. From this we get minus 14 by 2, which is minus 7. So we get B as minus 7. And then let us consider this element B plus C equal to 0 so that we can find C. B plus C equal to 0 implies C equal to minus B. We already got B as minus 7, so it is equal to 7. So C is 7. And now we have the last element which is left out, C plus D, it is equal to 8. C plus D equal to 8 implies D is equal to 8 minus C. So we already got value for C, it is 8 minus 7. So it is equal to 1. So D equal to 1. Therefore, A equal to 14, B equal to minus 7, C equal to 7, and D equal to 1. So these are the values of A, B, C and D. And now let us move on to the next exercise, which is exercise B. The first question, complete the following table. So here we have to complete this table with respect to the order of the matrix. So sometimes order of A, B is given, we have to find order of A plus or minus B, order of A, B, or sometimes the order of the matrices A plus or minus B or A, B is given. Accordingly, we have to fill the gaps. So the first one is, here it is given order of A is 2 by 2 and order of B is 2 by 2. Here we can see that the order of A and B are equal. So A plus or minus B is defined. And order of A plus or minus B will be equal to order of A or order of B. So this is equal to 2 by 2. And next we have order of AB. Here we can see that A and B are square matrices. So AB is also defined. And order of AB will also be equal to 2 by 2. And next we have the next situation where order of A is 2 by 3, order of B is 3 by 2. Here since order of A is not equal to order of B, A plus or minus B is not defined. So here we cannot find the order of this matrix. This is not possible. And next we have AB. Here we can see that the number of columns in A, it is equal to the number of rows in B. So order of AB is defined and order of AB is given by, this is the number of rows and this is the number of columns. So it is 2 by 2. Next we have the next one, order of A is 3 by 4, order of B is 4 by 1. Here again order of A not equal to order of B. So this is not possible. And then next we have AB. Here we can see that number of columns in A is equal to number of rows in B. So we can find AB. And AB has 3 rows and 1 column. So order of AB is 3 by 1. And next we can see that A and B are square matrices of order 3 by 3. So order of A plus or minus B will also be 3 by 3 and order of AB will also be 3 by 3. And next here we have order of A given as 2 by 3 and order of A plus or minus B is given as 2 by 3. So if order of A plus or minus B is 2 by 3, then order of B should be equal to order of A. So it is also 2 by 3. And now if we consider AB, here number of columns in A is not equal to number of rows in B. So here AB is not defined and this is not possible. We cannot find AB. And now we have the next situation where order of B is 3 by 2 and order of AB is 1 by 2. Now AB will be defined only when the number of columns in A is equal to the number of rows in B. Here the number of rows in B is 3. So the number of columns in A, it is 3. So this is 3. And next we have the number of rows given by number of rows in AB. So it is 1. So order of A is 1 by 3. Here order of A is 1 by 3, order of B is 3 by 2. Since their orders are not equal, A plus or minus B is not defined and this is not possible. And next we have now this is same as this one. So here order of A is 2 by 3, B is also 2 by 3 and finding AB is not possible. And next we have order of A is 1 by 3, order of B is 3 by 2. So here we can see that order of A not equal to order of B. So we cannot find A plus or minus B. This is not possible. And next we have AB. We can find AB when number of columns in A is equal to number of rows in B. Here they are equal. It is equal to 3. So order of AB will be 1 by 2. So it is 1 by 2. So this is same as this option. Next question, for A equal to this matrix, B equal to this given matrix and C equal to this given matrix, show that commutative property does not hold true for multiplication of matrices A and B. So let us finish the first subdivision and then let us proceed to the next subdivision. So here we have to show that AB not equal to BA. So this is commutative property for multiplication of matrices. We have to show that it does not hold true. So we have to prove that AB is not equal to BA. So first let us find AB. First subdivision. So AB is the product of A and B. So here this is 6 plus 10, multiplying first row first column, then first row second column, minus 18 minus 20, then second row first column, then second row second column. So this is equal to 16 minus 38 minus 15 and 37. So this is AB. Let us take this as 1. And now let us find BA. BA, it is this matrix B into matrix A. So it is the product of 1 minus 3 minus 2 4 and 6 minus 5 minus 7 4. Now this let us multiply first row first column. So it is 6 plus 21 minus 5 minus 12 minus 12 minus 28, then 10 plus 16. So this is equal to 27 minus 17 minus 40 and 26. So this is BA. So here we can see that from 1 and 2, AB is not equal to BA. From 1 and 2, AB not equal to BA. So commutative property does not hold true for multiplication of matrices. The next one is, we have the second subdivision. We have to show that associative property holds true for multiplication of 3 matrices. That is, we have to show that A into BC equal to AB into C. So for that, first let us take the left hand side. First let us find the product BC and then let us multiply A with the resulting product. And then let us find the right hand side. So this is the second subdivision. Left hand side is A into BC. So first let us consider BC. BC is the matrix B into the matrix C. So this is minus 2 minus 9, first row for first column, then first row second column 1 plus 3, then second row first column, second row second column. So this is minus 11, 4, 16, minus 6. This is BC. Now let us find A into BC. A into BC, it is the matrix A6 minus 5 minus 7 4 into the matrix which we just now got, minus 11 4 minus 16 and minus 6. So this is minus 66 minus 80 minus 146, and then it is 24 plus 30 54, and then it is 77 plus 64 141, and here it is minus 28 minus 24 minus 52. So this is A into BC. Now let us find AB into C. So the right hand side is AB into C. So first let us consider AB. So AB we just now calculated. So it is 6 plus 10, 16. Then minus 18 minus 20 minus 38. Then minus 7 minus 8 minus 15. Then 21 plus 16, 37. This is AB. And next we have AB into C. So this is 16 minus 38 minus 15, 37 into C. C is minus 2, 1, 3, minus 1. So this is 16 into minus 2 minus 32 minus 38 into 3, 114. Then 16 plus 38 and then 30 plus 111 and then minus 15 minus 37. So this is minus 146, 54, 141 and minus 52. So this is equal to the left hand side. Therefore, associative property holds true for multiplication of matrices. That is, A into BC is equal to AB into C. Next question. Consider A equal to this 3 by 3 matrix. 1, 3, 4, minus 2, 1, 2, 3, minus 2, 1. Verify that A into I equal to I into A equal to A, where I is the identity matrix of order 3 by 3. So here we have to verify that A into identity matrix equal to identity matrix into A equal to A. So first let us consider A into I. So A into I is, this is A, the given matrix, and I is the identity matrix. So if we multiply this, first row first column 1 plus 0 plus 0, then first row second column 0 plus 3 plus 0, then first row third column 0 plus 0 plus 4. And next we have second row first column minus 2 plus 0, then second row second column it is 1, second row third column 0 plus 0 plus 2, then third row first column 3 plus 0 plus 0, third row second column 0 0 minus 2 plus 0. Then third row, third column is 0 plus 0 plus 1. So here we can see that this is equal to k. This is a into I. Let us take this as 1. Now let us find I into a. So this is I into a. If we multiply these two matrices, first row, first column, only the first element will be there, the others are 0. Then first row, second column, again the first element only, it is 3. First row, third column, 4. Then second row, first column, only this second element will be there. 0 into 1, 0, 1 into minus 2, plus 0. Then second row, second column, if we multiply, it is 1. Second row, third column, 4 into 0, 0, plus 2 plus 0, so it is 2. Then third row, first column, it is 3. Third row, second column, minus 2. Third row, third column, 1. Again, this is equal to a. This is I into a. So from 1 and 2, a into I equal to I into a equal to a. Next question. If A is this 2 by 2 matrix 1 minus 3 minus 2 4 and B is 2 minus 4 minus 1 3, then show that. So we have to prove these two. The first one is we have to show that A plus B the whole transpose equal to A transpose plus B transpose. So first let us consider A plus B. The first one, left hand side is A plus B the whole transpose. So let us first find A plus B. Consider A plus B equal to the sum of A and B. This is matrix A and this is matrix B. So this is 3 minus 3 minus 4 minus 7 minus 2 minus 1 minus 3 4 plus 3 7. This is A plus B. Now A plus B the whole transpose, it is equal to first row becomes the first column and second row becomes the second column. So this is A plus B the whole transpose. Now let us take the right hand side. The right hand side is A transpose plus B transpose. It is equal to A transpose is the transpose of this matrix. So the first row becomes the first column and second row becomes the second column. Plus B transpose is the transpose of this matrix. So it is first row becomes the first column, second row becomes the second column. So this is 3 minus 7, 7. So this is equal to the left hand side. Therefore, A plus B the whole transpose, it is equal to A transpose plus B transpose. Moving on to the next question. The next subdivision, AB the whole transpose is equal to B transpose into A transpose. So we have to show that this is also true. So first let us take the left hand side, AB the whole transpose, and then first let us multiply A and B, then find the transpose, and then let us find B transpose and A transpose. Second one, left hand side is equal to AB the whole transpose. So first let us consider A into B. Consider AB. It is equal to product of these two matrices. 1 minus 3 minus 2 4 into 2 minus 4 minus 1 3. So this is 2 plus 3 5, then minus 4 minus 9 minus 13. And next we have minus 4 minus 4 minus 8, then 8 plus 12 20. So this is AB. AB the whole transpose. It is the first row becomes the first column and second row the second column. So this is AB the whole transpose. Now let us find B transpose into A transpose. Right hand side is B transpose into A transpose. It is, so here B transpose is first row becomes the first column, second row becomes the second column, and A transpose is first row becomes the first column, second row becomes the second column. So this is A transpose. Now if we multiply these two, it is 2 plus 3, 5, and then minus 4, minus 8, and minus 4, minus 9, minus 13, then 8 plus 12, 20. So this is equal to the left hand side. Therefore, AB the whole transpose equal to B transpose A transpose. Next we have the next question, do as directed. So we have to find whatever is asked. For A equal to 6 minus 5 minus 7, 4. Find A square minus 6A. So first we have to find A square and then let us find A square minus 6A. So here we have to find A square minus 6A. Consider A square as, A square is nothing but it is A into A. So it is, A is this matrix. So it is the same matrix twice. So this is 36 plus 35, then minus 30 minus 20, then minus 42 minus 28, then 35 plus 16. So this, when we simplify, we get it as 71 minus 50 minus 70 and 51. Now let us find A square minus 6A. So A square minus 6A. A square, we just now got this matrix minus 6 into A. So it is 71 minus 50 minus 70, 51 minus 36 minus 42 minus 30, 24. So this is 71 minus 36, 35, minus 50 plus 30 minus 20, then minus 70 plus 42 minus 28, 51 minus 24, 27. So this is A square minus 6A. Next question, evaluate. We have to find the value of this matrix. So it is 2, 1, 3, minus 1, minus 1, 0, 0, 1, 1, minus 1, 0, 1, then 1, 0, minus 1. So here we can see that the order of this, it is 1 by 3 and the order of this matrix is 3 by 3. So here we can multiply these two matrices and we can obtain a matrix of order 1 by 3. So let us take, let A equal to the given matrix. So this is equal to first row, first column. So minus 2, minus 1 plus 0, it is minus 3. Then first row, second column, 0 plus 1 plus 3, 4. Then first row, third column, minus 2 plus 0 plus 3, it is 1. Into 1, 0, minus 1. So this is a matrix of order 1 by 3 and this is a matrix of order 3 by 1. So we will get a matrix of order 1 by 1. So this is minus 3 into 1 plus 4 into 0, 0 plus 1 into minus 1, minus 1. So this is minus 4. So the value of this matrix is the matrix minus 4. Next question, find a matrix A such that this matrix 1, 2, minus 1, 0, 4, 9, it is equal to 9, minus 1, 4, minus 2, 1, 3, minus A. So we have to find A such that this equality will hold. So here, if we have this condition, A will be this matrix 9, minus 1, 4, minus 2, 1, 3, minus of this matrix. So A equal to this matrix minus 1, 2, minus 1, 0, 4, 9. So this is 9 minus 1, 8, minus 1, minus 2, minus 3, 4 plus 1, 5, minus 2, minus 0, minus 2, 1 minus 4, minus 3, 3 minus 9, minus 6. So this is A. Next question, if the matrix X is equal to minus 1, 0, 5, 13 is equal to the matrix Y equal to P minus Q, 2P plus R, 2P minus Q, 3R plus S. Then find the value of P, Q, R and S. So here it is given these two matrices are equal. So we can compare each of the values. We can equate each element to the corresponding element of the other matrix and we can find the values of P, Q, R and S. So here given X is equal to Y. So this implies this matrix, it is equal to Y. So we can compare the elements. Comparing. Here we will have P minus Q equal to minus 1. P minus Q equal to minus 1 and 2P minus Q equal to 0. 2P minus Q equal to 0. Now if we subtract these two equations, we will get minus P equal to minus 1. Here P minus 2P will be minus P. Minus Q plus Q will go, it will become 0. Minus 1 minus 0 is minus 1. So we get P as 1. So if P is 1, we can substitute P as 1 here. So this implies 2 minus Q equal to 0 or Q equal to 2. And now we can compare 2P plus R equal to 5. 2P plus R equal to 5 implies, we already got P as 1, 2 plus R equal to 5. So R equal to 5 minus 2, which is 3. Next we have 3R plus S equal to 13. 3R plus S equal to 13 implies we already got R as 3. So 3 into 3 plus S equal to 13. So S will be 13 minus 9, which is 4. Therefore, we get the values of P as 1, Q as 2, R as 3 and S as 4. So these are the values of P, Q, R and S. Next question, let P equal to 2 minus 1, 3, 1 and Q equal to 1, 4, 7, 2. Then calculate 3P minus 2Q. So we have to find the value of 3P minus 2Q. So 3P minus 2Q is equal to 3 into P minus 2 into the matrix Q. So this is 6 minus 3, 9, 3 minus 2, 8, 14, 4. So it is 6 minus 2, 4, minus 3 minus 8 minus 11, 9 minus 14 minus 5, 3 minus 4 minus 1. So this is 3P minus 2Q. Next we have, if A is 804 minus 236 and B is 2 minus 242 minus 51, then find a matrix C such that 3A minus 2B plus 4C equal to 0. So here we have to find a matrix C which satisfies this condition. Since 3A minus 2B plus 4C equal to 0, we have 4C as 2B minus 3A. So using this relation, we can find C, or C is 1 by 4 into 2B minus 3A. So from here we have 4C equal to 2 into the matrix B. This is matrix B minus 3 into matrix A. This is matrix A. So this is 4 minus 4, 8, 4 minus 10, 2 minus 24, 0, 12 minus 6, 9, 18. So this, when we subtract, it is 4 minus 4 minus 20, then minus 4 minus 0, then 8 minus 12 minus 4, then 4 plus 6, 10, then minus 10 minus 9 minus 19, then 2 minus 18 minus 16. So from this we get C as 1 by 4 into this matrix, minus 20 minus 4 minus 4 minus 10 minus 19 minus 16. So we can divide each term by 4. We get minus 5 minus 1 minus 1. 10 by 4 it is 5 by 2. Minus 5 by 2. Then minus 19 by 4. This is plus 10. So it is plus 5 by 2. And minus 4. 16 by 4 is 4. So this is C. This is the matrix C. Next question, given A equal to 1 minus 1 0 2 3 4 0 1 2, B equal to 2 2 minus 4 minus 4 2 minus 4 2 minus 1 5. Find, we have to find each of these matrices. So first let us find 2A minus 3B. So this is the first subdivision, 2A minus 3B. So 2A minus 3B, it is nothing but 2 into matrix A minus 3 into matrix B. So this is matrix A and this is matrix B. So this is 2 minus 2, 0, 4, 6, 8, 0, 2, 4. Minus 6, 6 minus 12, minus 12, 6 minus 12, 6 minus 3, 15. So it is 2 minus 6 minus 4, then minus 2 minus 6 minus 8, then 0 minus of minus 12 plus 12, 4 plus 12, 16, 6 minus 6, 0, 8 plus 12, 20, 0 minus 6 minus 6, 2 plus 3, 5, and 4 minus 15 minus 11. So this is the matrix 2A minus 3B. Next we have the, now let us find matrix A into B. So the second subdivision we have to find AB. It is product of A and B. AB equal to, this is matrix A and this is matrix B. So this is equal to, it is 2 plus 4 plus 0, 6. Then 2 minus 2 plus 0, 0. Then it is minus 4 plus 4 plus 0, 0. Then it is 4 minus 12 plus 8, 0. It is 4 plus 6 minus 4, which is 6. Then it is minus 4 minus 12 plus 20. So it is 0. Next it is 0 minus 4 plus 4. Again 0 here. Next we have 0 plus 2 minus 2, which is again 0. So 0. And next 0 minus 4 plus 10. So 10 minus 4 is 6. So this is matrix AB. Next we have the next subdivision BA. So matrix BA, the third subdivision BA is, this is matrix B into matrix A. So this is, it is 2 plus 4 plus 0, 6. And next we have minus 2, minus 6. Minus 2 plus 6 minus 4, which is 0. Then 0 plus 8 minus 8. So it is 0. Next we have minus 4 plus 4 minus 0, 0. Then 4 plus 6 minus 4, it is 6. Then 0 plus 8 minus 8, 0. Then it is 2 minus 2 plus 0, it is 0. Then it is minus 2 minus 3 plus 5, which is 0. Next we have 0 minus 4 plus 10. So 10 minus 4 is 6. So this is BA. So here we can see that AB and BA are equal. The last subdivision we have to find AB minus BA. So here AB minus BA, it is the difference of these two matrices, which is nothing but the 0 matrix. Minus 6 0 0 0 6 0 0 0 6. So this is 0. Or it is equal to the 0 matrix. AB minus BA equal to 0 matrix. Now let us proceed. For A equal to 1 2 3, 3 minus 2 1, 4 2 1, show that A cube minus 23A minus 40I equal to O, where I is an identity matrix of order 3 and O is the 0 matrix. So we have to show that when A is this matrix, A cube minus 23A minus 40I, it is equal to the 0 matrix. So first let us find A cube. A cube, it is nothing but A square into A. This A square is A into A. So first let us find A square. So A square is A into A. It is matrix A into matrix A. So here let us multiply these two matrices. So it is 3 plus 6 plus 12, and then it is 2 minus 4 plus 6, and then it is 3 plus 2 plus 3, and here we have 3 minus 6 plus 4. Next we have 6 plus 4 plus 2, and then we have 9 minus 2 plus 1. Here it is 4 plus 6 plus 4. Here it is 8 minus 4 plus 2, and then it is 12 plus 2 plus 1. So this is 19, 4, 8, 1, 12, 8, 14, 6, 15. So this is A square. Now we have A cube. A cube is A square into A. A square we just now found. 19, 4, 8, 1, 12, 8, 14, 6, 15 into A. 1, 2, 3, 3 minus 2, 1, 4, 2, 1. So this is 19 plus 12 plus 32. Then it is 38 minus 8 plus 16. Then it is 57 plus 4 plus 8. And then we have 1 plus 36 plus 20 plus 32. And then we have 2 minus 24 plus 16. And then it is 3 plus 12 plus 8. Next we have 14 plus 18 plus 60, then 28 minus 12 plus 30, and then 42 plus 6 plus 15. So this, when we simplify, we get 63, 46, 69, then 69 minus 6, 23, 92, 46 and 63. So this is a cube. So here we need to have a cube minus 23a minus 40i. LHS is a cube minus 23a minus 40i. So it is 63, 46, 69, 69 minus 6, 23, 92, 46, 63 minus 23 into a. So this is minus 23 into a. So it is 23, 46, 69, 69 minus 46, 23, 92, 46, 23 minus 40 into I. So 40 into I is the identity matrix. So it is nothing but 40, 0, 0, 0, 40, 0, 0, 0, 40. So here we get 63 minus 23, 40 minus 40, 0. Then 46 minus 46, 0. Then 69 minus 69, 0. Then here 69 minus 69 minus 0, 0. Then minus 6 plus 46 is plus 40, minus 40, 0. Then 23 minus 23, 0. Then 92 minus 92 minus 0, 0. Then 46 minus 46 minus 0, 0. Then 63 minus 23 is 40, minus 40 is 0. So this is equal to the 0 matrix, which is equal to the right hand side. Moving on to the next question. Ninth question. Here is a word problem on matrix. Two booksellers A and B sell the textbook of mathematics and applied mathematics. In the month of March, bookseller A sold 250 books of mathematics and 400 books of applied mathematics, whereas bookseller B sold 230 books of mathematics and 425 books of applied mathematics. In the month of April, bookseller A sold 550 books of mathematics and 300 books of applied mathematics, and bookseller B sold 270 books of mathematics and 450 books of applied mathematics. Represent the given information into matrix form and find the total sale for both the booksellers in the month of March and April using matrix algebra. So here we have two booksellers A and B, and they sell math books and applied math books. So in the month of March, A sells 250 math books and 400 applied math books. B sells 230 math books and 425 applied math books. This is for March. Then in April, A sells 550 math books and 300 applied math books. B sells 270 math books and 450 applied math books. So we have to represent this in the form of a matrix, and we have to find the total sale for both the booksellers in the month of March and April. So here let us take sale in March B, the matrix P. Sale in March P equal to the matrix 250, 400, 230, 425. So this is with respect to A and this is with respect to B. And next we have sale in April. Let us take this as matrix Q. Matrix Q, it is 550, 300, 270, 450. So first row corresponds to bookseller A and second row to bookseller B. Now total sales, it will be P plus Q. It is P plus Q. So it is the sum of these two matrices. So it is matrix P plus matrix Q. So P plus Q. This is equal to 250 plus 550, 800, 400 plus 300, 700, 230 plus 270, 500, 425 plus 450, 875. So this is the total sales for A and B. Therefore, total sales equal to the last question in this exercise, cost of a pen and a notebook are rupees 12 and rupees 27 respectively. On a given day, shopkeeper P sells 5 pens and 7 notebooks, whereas shopkeeper Q sells 6 pens and 4 notebooks. Find the income of both the shopkeepers using matrix algebra. So here the cost of a pen and a notebook are given and the number of pens and notebooks which shopkeepers P and Q sell are given. We need to find the income of both the shopkeepers using matrix algebra. So let cost be the matrix C, which is 12 and 27. And then let us take the matrix for sales as S. So P sells 5 pens, 7 notebooks, Q sells 6 pens, 4 notebooks. So this is P and this is Q. Income I, it is equal to S into C. So it is 5764 into 1227. So this is 60 plus 189 and then 72 plus 108. So it is 249 and 180. So this is for shopkeeper P and this is for shopkeeper Q. Therefore, income of shopkeeper P is rupees 249 and income of shopkeeper Q is 180. So this is the income of shopkeeper P and this is the income of shopkeeper Q. Now moving on to the next exercise, which is on determinants. The first one, evaluate the following. So the first one is determinant of 4 minus 2, 6 minus 3. So this is 4 into minus 3 minus 12 minus 6 into minus 2 minus 12. So this is minus 12 plus 12, which is 0. Then the next question, determinant of 7, 1, 4 minus 7. So this is minus 7 into 7 minus 49 minus 1 into 4, 4. So it is minus 53. And next we have the next question, determinant of 3, 1 minus 1, 8. So it is 8 into 3, 24, minus of minus 1 plus 1. So it is 25. Next we have the next question, determinant of minus 3, minus 1, 2, 5, 7, minus 8, minus 2, minus 6, 6. So here we can apply some of the properties of determinant and we can simplify. So here applying R1 changing to R1 plus R2. So delta will be equal to, here minus 3 plus 5, it is 2. Then minus 1 plus 7, 6. Then 2 minus 8, minus 6. The other rows remain the same. Here we can see that the first row and the third row, it is in the ratio minus 1 is to 1. So the value of this determinant, it is equal to 0, since R1 by R3 equal to minus 1. So this is the value of this determinant. Next we have the next question, determinant of 1, 2, 1, 1, 0, 3, 2 minus 3, 0. So here let us expand along C3. So if we expand along C3, then it will be easy since there is 1, 0 here. So we get delta equal to 1 into minus 3 minus 0, minus 3 into minus 3 minus 4 plus 0 into it is 0. So here it is minus 3 plus 21. So this is equal to 18. So the value of this determinant, it is equal to 18. Moving on to the next question. Find the area of the triangle with vertices minus 2, minus 3, minus 1, minus 8 and 3, 2. So area of triangle equal to half of determinant of x1, y1, 1, x2, y2, 1, x3, y3, 1. Where x1, y1 is the first vertex, x2, y2 is the coordinate of the second vertex and x3, y3 is the coordinate of the third vertex. So this is half of minus 2, minus 3, 1, minus 1, minus 8, 1, 3, 2, 1. So let us expand along R1. Expanding along R1. So delta equal to half of minus 2 into minus 8 minus 2 minus 10, minus of minus 3 is plus 3, minus 1 minus 3 minus 4 plus 1 into minus 2 plus 24. It is 22. So this is half of, here it is 20, 20 minus 12 plus 22. So it is 30. This is equal to 15. So area of the triangle equal to 15. 15 square units. Next question, for what value of k the points k7, minus 4, 5 and 1, minus 5 are collinear. So we know that if 3 points are collinear, then the area of the triangle is equal to 0. So first let us write the formula for area of the triangle and equate that to 0. Area of triangle equal to x1, y1, 1 half into determinant of x2, y2, 1, x3, y3, 1. This is equal to 0 since points are collinear. So this implies half of k7, 1 minus 4, 5, 1, 1 minus 5, 1. it is equal to 0. So this part alone will be equal to 0. So let us expand along R1. Expanding along R1. We get k into 5 plus 5 10 minus 7 into minus 4 minus 1 minus 5 plus 1 into 20 minus 5 15. This is equal to 0. So 10k, here it is the 35 plus 15 plus 50 equal to 0. So we get 10k as minus 50, k equal to minus 50 by 10, which is minus 5. So k is minus 5. Next question, represent the given matrices as sum of symmetric and skew symmetric matrix. So here let us take, let the given matrix be A. So we can express A as sum of symmetric and skew symmetric matrix as A equal to half of A plus A transpose plus half of A minus A transpose. This is A plus A transpose is symmetric and A minus A transpose is skew symmetric. So we have, let P equal to half of A plus A transpose. So it is half of A is 3, 1 minus 1, 8 plus A transpose is the first row becomes the first column and the second row becomes the second column. This is A transpose. So this is half of 3 plus 3 6, 1 minus 1 0, minus 1 plus 1 0, 8 plus 8 16. So this is 3 0 0 8. Now this is symmetric. Equal to P transpose implies P is symmetric. Next, let us have Q as half of A minus A transpose. So this is half of A is 3, 1 minus 1, 8 minus A transpose is 3 minus 1, 1, 8. So this is half of 3 minus 3, 0, 1 minus of minus 1 plus 1. So it is 2, minus 1 minus 1 minus 2, 8 minus 8, 0. So this is 0, 1, minus 1, 0. Now the transpose of this is Q transpose is 0, 1, minus 1, 0. It is equal to minus Q implies Q is skew symmetric. Therefore, A equal to P plus Q implies A equal to P is 3, 0, 0, 8 plus Q is 0, 1, minus 1, 0. If we add these two, we will get A. This is symmetric and this is skew symmetric. Next question, we have to represent the given matrix as sum of symmetric and skew symmetric. So this is minus 4, 4, 4, minus 7, 1, 3, 5, minus 3, minus 1. So let us take this as equal to A. Now A equal to half of A plus A transpose plus half of A minus A transpose. So let us take, let P equal to half of A plus A transpose. So it is half of A is the given matrix and A transposes, the rows become columns. Minus 4, 4, 4, minus 7, 1, 3, 5, minus 3, minus 1. So this is half of minus 4 minus 4 minus 8, 4 minus 7 minus 3, 4 plus 5 9, minus 7 plus 4 minus 3, 1 plus 1 2, 3 minus 3 0, 5 plus 4 9, minus 3 plus 3 0, minus 1 minus 2. So we get P is equal to minus 4 minus 3 by 2, 9 by 2, minus 3 by 2, 1 0, 9 by 2, 0, minus 1. So this is equal to P transpose, implies P is symmetric. And next let us take, let Q is equal to half of A minus A transpose. So this is half of A is the given matrix minus A transpose is the transpose of A. So this is half of minus 4 minus of minus 4 is plus 4. So 0. Then 4 plus 7 it is 11. Then 4 minus 5 minus 1. Then minus 7 minus 4 minus 11. 1 minus 1 0. 3 plus 3 6. 5 minus 4 1. Minus 3 minus 3 minus 6. Minus 1 plus 1 0. This is 0, 11 by 2 minus 1 by 2, minus 11 by 2, 0, 3, 1 by 2, minus 3, 0. This is a skew symmetric matrix. This is equal to negative Q transpose. Therefore, A equal to P plus Q, which is equal to P is minus 4 minus 3 by 2, 9 by 2, minus 3 by 2, 1, 0, 9 by 2, 0, minus 1, which is a symmetric matrix, plus Q is 0, 11 by 2, minus half, minus 11 by 2, 0, 3, half, minus 3, 0. So we have expressed A as sum of symmetric and skew symmetric matrix. Next question, we have to express this matrix as sum of symmetric and skew symmetric matrix. So let us take the given matrix as equal to A. So we have A equal to half of A plus A transpose plus half of A minus A transpose. Now this A plus A transpose is symmetric and A minus A transpose is skew symmetric. So let us take, let P equal to half of A plus A transpose. So it is half of minus 2 0 1 9 2 minus 3 6 1 minus 2 plus transpose of this. First row becomes first column, second row second column, and third row third column. So this is half of minus 2 minus 2 minus 4, 0 plus 9 9, 1 plus 6 7, 9 plus 0 9, 2 plus 2 4, minus 3 plus 1 minus 2, 6 plus 1 7, 1 minus 3 minus 2, minus 2 minus 2 minus 4. So this is minus 2, 9 by 2, 7 by 2, 9 by 2, 2 minus 1, 7 by 2 minus 1 minus 2. So this is equal to P, which is equal to P transpose, implies P is symmetric. And next we have, let us take let Q equal to half of A minus A transpose. So here we have A and here we have A transpose. So let us subtract these two. So this is equal to half of minus 2, 0, 1, 9, 2, minus 3, 6, 1, minus 2, minus A transpose. Minus 2, 0, 1, 9, 2, minus 3, 6, 1, minus 2. So this is half of minus 2 plus 2, 0, 0 minus 9, minus 9, 1 minus 6, minus 5, 9 minus 0, 9, 2 minus 2, 0, minus 3 minus 1, minus 4, 6 minus 1, 5, 1 plus 3, 4, minus 2 plus 2, 0. So this is equal to 0 minus 9 by 2, minus 5 by 2. 9 by 2, 0, minus 2, 5 by 2, 2, 0. So if we find the transpose of Q, the first row becomes the first column, the second row becomes the second column, and the third row becomes the third column. So this is equal to minus Q, which implies Q is skew symmetric. So we can write A as P plus Q. Therefore, A equal to P plus Q implies A equal to minus 2, 9 by 2, 7 by 2, 9 by 2, 2 minus 1, 7 by 2 minus 1 minus 2 plus Q. Here P is symmetric and Q is skew symmetric. 0 minus 9 by 2 minus 5 by 2, 9 by 2, 0 minus 2, 5 by 2, 2, 0. So if we add these two matrices, we will get the matrix A. Moving on to the next question, evaluate using properties of determinants. So this is the first one, determinant of this we have to find. So let us take this as equal to delta, and then let us do applying C1 changing to C1 plus C2 plus C3. So here we will have B minus C plus C minus A plus A minus B. Then C minus A plus A minus B plus B minus C. Then A minus B plus B minus C plus C minus A. The other columns remain the same. So here we can see that B minus B minus C plus C minus A plus C cancel. C minus C minus A plus A minus B plus C 0. A minus A minus B plus C minus C plus C. So it is 0. The first column becomes 0. So this is 0, 0, 0. C minus A minus B, B minus C. A minus B, B minus C, C minus A. So this is equal to 0. If any one column or row is 0, then the value of the determinant is equal to 0. Therefore, delta equal to 0. Next we have the next question. The second and third are same. So let us solve any one. Determinant of x plus y plus z, x plus z, zxy, 1, 1, 1. So let us take this as equal to delta. So here applying R1 changing to R1 plus R2. So delta becomes x plus y plus z. Then y plus z plus x, we can write it as x plus y plus z. Then x plus z plus y, we can write it as x plus y plus z. Zxy, 1, 1, 1. Again, this is equal to 0 since R1 by R3. It is in the ratio x plus y plus z is to 1. So the value of this determinant, it is also equal to 0. The third one is the same. Fourth one, determinant of 265, 240, 219, 240, 225, 198, 219, 198, 181. So here let us applying R1 changing to R1 minus R2 and R2 changing to R2 minus R3. We get delta as 265 minus 240, 25, 240 minus 225, 15, 219 minus 198, 21. Then R2 minus R3, 240 minus 219, 21, 225 minus 198, 27, 198 minus 181, 17. Now let us apply R1 changing to R1 minus R2 and R3 changing to R3 minus 10R2. So we get delta as 25 minus 21, 4, 15 minus 27 minus 12, 21 minus 17, 4. Then R2 remains the same. Next R3 changing to R3 minus 10 R2. So 219 minus 210, 9. Then 198 minus 270. So 270 minus 198. So it is minus 72. Then 181 minus 170. It is 11. Next let us apply C2 changing to C2 plus 3 C1 and C3 changing to C3 minus C1. So delta becomes C1 remains the same. C2 is C2 plus 3 C1. So minus 12 plus 12, 0. Then 27 plus 63, 90. Then minus 72 plus 27. So 72 minus 27 is 45. So minus 45. Next we have C3 changing to C3 minus C1. 4 minus 4, 0. 17 minus 21 minus 4. 11 minus 9 is 2. So let us expand along R1. So delta will be 4 into 90 into 2 is 180 minus 45 into 4 is 180. So this is equal to 0. Therefore, the value of the given determinant is equal to 0. Next question. We have determinant of a, b, c, a plus 2x, b plus 2y, c plus 2z, then x, y, z. So let us take this as equal to delta and then applying R1 changing to R1 plus 2 R3. So delta will be a plus 2x, b plus 2y, c plus 2z. then the second row and the third row will be the same. X, Y, Z. Now this is equal to 0. Since we know that if any two rows or into columns are equal, then the value of the determinant is equal to 0. Next, we have proved the following using properties of determinants. So we have to prove the determinant of minus a square ab minus b square bc, ac bc minus c square equal to 4a square b square c square. So let us take let delta equal to the left hand side, minus a square ab ac, ab minus b square bc, ac bc minus c square. So here let us take a common from C1, b common from C2 and c common from C3. Taking a, b, c common from C1, C2, C3 respectively. Delta equal to a, b, c into, so here we have a minus a, b, c, then here a minus b, c, and here it is a, b minus c. And now we can take a common from first row, b common from second row and c common from third row. Taking a, b, c common from R1, R2, R3 respectively. So we have delta as ABC into ABC into determinant of minus 1, 1, 1, 1 minus 1, 1, 1, 1 minus 1. So this will be a square, b square, c square. We can expand along R1. Expanding along R1 into, so minus 1 into 1 minus 1, 0, minus 1 into minus 1 minus 1 plus 1 into 1 plus 1. So this is, so here we have minus 1 into minus 2 is 2 plus 2, 2 plus 2, 4. So this is equal to 4a square, b square, c square. This is equal to the right hand side. So this is what we have to prove. Now moving on to the next question. We have to prove the determinant of 1, 1, 1, 1, 1 plus 6, 1, 1, 1, 1 plus y. It is equal to xy. So let us perform applying R2 changing to R2 minus R1 and R3 changing to R3 minus R1. So we get left hand side as first row remains the same, 1 minus 1 0, 1 plus x minus 1 x, 1 minus 1 0. Then here 1 minus 1 0, 1 minus 1 0, 1 plus y minus 1 y. Now here let us expand along C1. Expanding along C1, delta equal to, so it is 1 into xy minus 0, 1 into xy, then all the other terms are 0. So this is equal to xy, which is equal to the right hand side. Next question, determinant of 1a square, 1b b square, 1c c square. This we have to prove that it is equal to a minus b into b minus c into c minus a. So let us perform applying R1 changing to R1 minus R2 and R2 changing to R2 minus R3. So let us take left hand side as delta. It becomes R1 minus R2, 1 minus 1, 0, a minus b, a square minus b square. Then 1 minus 1, 0, b minus c, then b square minus c square, 1c c square. So here we can see that here a minus b is common in R1 and b minus c is common in R2, which can be taken outside. So taking a minus b common from R1 and b minus c common from R2. So delta becomes a minus b into b minus c into, here we are left with 0, 1, a square minus b square, you can write it as a minus b into a plus b. So a minus b is already outside. Here we have a plus b. Then here 0, 1. Similarly here we have b plus c. 1c c square. So we can expand along C1. Expanding along C1, we get delta as a minus b into b minus c into, here these two terms are 0, so 0 plus 0, then plus 1 into b plus c minus a minus b. So plus b minus b will go. So this is equal to a minus b into b minus c into c minus a, which is equal to the right hand side. Therefore, left hand side equal to the right hand side. Next question, determinant of alpha beta gamma, alpha square beta square gamma square, beta plus gamma, gamma plus alpha, alpha plus beta. This should be equal to alpha minus beta, beta minus gamma, gamma minus alpha into alpha plus beta plus gamma. So here let us perform applying C1 changing to C1 minus C2 and C2 changing to C2 minus C3. So the left hand side is delta equal to C1 minus C2 alpha minus beta, alpha square minus beta square, and then beta plus gamma minus alpha. And here we have beta minus gamma, beta square minus gamma square. Here we have gamma plus alpha minus beta. Gamma, gamma square, alpha plus beta. So plus gamma minus gamma will go, plus alpha minus alpha will go. Here we can see that alpha minus beta is common and here beta minus gamma is common, which can be taken outside. Taking alpha minus beta and beta minus gamma common from C1 and C2 respectively. So we get delta as alpha minus beta into beta minus gamma into, here we will have 1 and here we will have alpha minus beta into alpha plus beta. So we already took alpha minus beta outside. So here it is alpha plus beta. And here since we have beta minus alpha, we will have minus 1. So it is 1 alpha plus beta minus 1. Similarly here it is 1 beta plus gamma and minus 1. Then gamma, gamma square, alpha plus beta. And now let us perform R1 changing to R1 plus R3, so that we will have 0, 0, then alpha plus beta plus gamma. So here R1 changing to R1 plus R3. So we have delta as alpha minus beta, beta minus gamma, then 1 minus 1 0, 1 minus 1 0. Here we will have alpha plus beta plus gamma. Then we have alpha plus beta, beta plus gamma, gamma square, minus 1, alpha plus beta. Now here we can take alpha plus beta plus gamma common outside from R1. Taking alpha plus beta plus gamma common from R1. So we get delta as alpha minus beta, beta minus gamma into alpha plus beta plus gamma into determinant of 0, 0, 1 alpha plus beta, beta plus gamma, gamma square, minus 1, alpha plus beta. Now we can expand along R1. Expand along R1. Into alpha plus beta plus gamma. Here we will have 0 into, so it becomes 0 plus 0 into 0, then plus 1 into minus alpha minus beta plus beta plus gamma. So we get this as alpha minus beta into beta minus gamma into gamma minus alpha into alpha plus beta plus gamma, which is equal to the right hand side. So this is what we have to prove, and we got it. Next question, we have to prove that determinant of 1, 1 plus p, 1 plus p plus q, 2, 3 plus 2p, 1 plus 3p plus 2q, 3, 6 plus 3p, 1 plus 6p plus 3q. This is equal to 1. So here let us apply R2 changing to R2 minus 2 R1 and R3 changing to R3 minus 3 R1. So delta is, first row remains the same. Second row 2 minus 2 0, and then we have 3p plus 2p minus 2 minus 2p. So it is 1, and next we have 1 plus 3p plus 2q minus 2 minus p minus 2p minus 2q. So here we will have minus 1 plus p. And next we have R3 changing to R3 minus 3 R1, 3 minus 3 0. Here it is 6 plus 3p minus 3 minus 3p. So it is 3. And then here we have 1 plus 6p plus 3q minus 3 minus 3p minus 3q. So it is minus 2 plus 3p. Now we can expand along C1. Expanding along C1. So delta will be equal to 1 into minus 2 plus 3p minus 3 into minus 1 plus p. The other terms are 0. So this is minus 2 plus 3p plus 3 minus 3p, which is equal to 1. So this is equal to 1, which is the right hand side. So this is what we have to prove, and we have proved. Next question, find adjoint of A if A equal to this matrix 2, 1, minus 3, 5. So if A is a 2 by 2 matrix, then adjoint of A is obtained by interchanging the diagonal elements and changing the sign of the other elements. So this is adjoint of A. The second question, A equal to minus 52, 11, 0, 51. So again it is a 2 by 2 matrix. So adjoint of A is, we have to change the diagonal elements, interchange the diagonal elements and change the sign of the other elements. So this is adjoint of A. Next question, find adjoint of A if A is this 3 by 3 matrix. So we know that if A is a 3 by 3 matrix, then adjoint of A is obtained by the transpose of the cofactor matrix. So adjoint of A is transpose of cofactor matrix. So let us find the cofactor first. Cofactor of this one is 6 minus 4, and then we have minus of cofactor of minus 1 is 2 into 2, 4 minus 0. Then cofactor of this element 0, it is 2 into 1, 2 minus 0. Then cofactor of this element 2 is, we have to delete the second row and the first column. So it is minus 2 minus 1, which is minus 2. Here it is minus of minus 2. Next we have cofactor of this element. It is obtained by deleting second row and the second column. So it is 2 minus 0, 2. Cofactor of 4 obtained by deleting second row and the third column with a negative sign. It is negative of 1. Here cofactor of 0, it is the determinant of this minus 1, 0, 3, 4, which is obtained by deleting first column and the third row. So it is minus 1 into 4, minus 4, minus 0. And next we have minus of cofactor of 1. It is obtained by finding the determinant by deleting the third row and the second column. So it is 1 into 4, 4 minus 0. So this is 4. Next we have cofactor of the last element 2. It is 3 plus 2, which is 5. The whole transpose. So this is 2 minus 4, 2. Then it is 2, 2 minus 1. Then it is minus 4, 5. The whole transpose. So adjoint of A. The first row becomes the first column. Second row becomes the second column. And the third row becomes the third column. So this is adjoint of A. So with this exercise is over. Let us move on to the next exercise. Next exercise, the first question, we have to find the inverse by elementary operations, which is not included in the syllabus. So let us move on from the second question. Find inverse of the given matrices by using adjugate or matrix method. The first one is 4 minus 1, 3, 2. So let us take this as equal to A, say. So we find the inverse of a matrix using matrix method by 1 by determinant of A into adjoint of A. So for that, first let us find determinant of A. Determinant of A, it is 8 plus 3, which is 11. This is not equal to 0. So A inverse exists. Implies A inverse exists. If it is equal to 0, we cannot find A inverse. So A inverse equal to 1 by determinant of A into adjoint of A. Adjoint of A is, it is a 2 by 2 matrix, so we can interchange the diagonal elements and change the sign of the other elements. So A inverse equal to 1 by 11 into 2, 1 minus 3, 4. So this is A inverse. Then the next subdivision, we have to find A inverse for this matrix. So let us take this as equal to A. Now determinant of A is expand along R1. So it is 2 into 0 plus 4, 4 plus 1 into 28 minus 6, 22 plus 4 into minus 8. So this is 30 minus 32, which is minus 2, not equal to 0. Therefore, A inverse exists. Now let us find adjoint of A. Adjoint of A, it is the transpose of the cofactor matrix. So here it is 0 plus 4, 4, then minus of 28 minus 6, 22, then it is minus 8. And here it is with a negative sign. It is minus 7 plus 8, 1. So minus 1. And next we have 14 minus 12, 2. And next here we have a negative sign. It is minus 4 plus 3, minus 1. And next we have minus 2. And here we have a negative sign. Next we have 4 minus 16, minus 12. And finally we have 0 plus 4, which is 4. This transpose. So here the first row becomes the first column. So it is 4 minus 22 minus 8. Then second row becomes the second column. And the third row becomes the third column. This is adjoint of A. So A inverse is 1 by determinant of A into adjoint of A. It is 1 by minus 2 into adjoint of A is 4 minus 1 minus 2 minus 22 2 12 minus 8 1 4. So if we divide each of these term by minus 2, we get it as minus 2 half 1 11 minus 1 minus 6 4 minus half minus 2. So this is A inverse. Moving on to the next question. Solve the following system of equations using matrix method. So we have to solve the system of equation using matrix method. The first subdivision, 2x minus 3y equal to minus 4, 3x plus 5y equal to 13. So the given system of equations can be written in the matrix form as Ax equal to B, where A equal to the coefficient matrix, that is 2 minus 3, 3, 5. Then X is the variable matrix X and Y, and B is the constant matrix minus 4 and 13. Now we have to find A inverse. So for that, first we have to find determinant of A. Determinant of A is 10 plus 9, 19, not equal to 0, implies A inverse exists. Then adjoint of A is it is a 2 by 2 matrix, so we can interchange the diagonal elements and change the sign of the other elements. This is adjoint of A. A inverse equal to 1 by determinant of A into adjoint of A. So it is 1 by 19 into 5, 3 minus 3, 2. Now Ax equal to B implies x equal to A inverse into B. So this implies x is equal to 1 by 19 into A inverse is this matrix 1 by 19 into 5, 3 minus 2. Minus 3, 2 into B. B is minus 4, 13. So this is 1 by 19 into 5 into minus 4 minus 20 plus 3 into 13 39, then minus 3 into minus 4 12 plus 13 into 2 26. So this is 1 by 19 into 39 minus 20 is 19, 12 plus 26 is 38. So x is nothing but the variable matrix x and y. This is equal to 19 by 19 1, 38 by 19 2. Therefore, x is equal to 1 and y is equal to 2. Now moving on to the next question. X plus y equal to 1, 5x minus 7y equal to 29. So here the given system of equations can be written in the matrix form as Ax equal to B, where A is the coefficient matrix, A equal to 1, 1, 5 minus 7. Then x is equal to the variable matrix xy, and B is the constant matrix 1, 29. So here again we have to find A inverse first. So for that, first let us find determinant of A. This is minus 5, minus 7 minus 5, which is minus 12. This is not equal to 0, which means A inverse exists. And next let us find adjoint of A. Adjoint of A is obtained by interchanging the diagonal elements and changing the sign of the other elements in A. So this is adjoint of A. Now A inverse equal to 1 by determinant of A into adjoint of A. So this is equal to minus 1 by 12 into minus 7, minus 1, minus 5, 1. And next we have to find x and y. Now Ax equal to B implies x is equal to A inverse into B, or x is equal to A inverse is minus 1 by 12 into minus 7 minus 1 minus 5 1 into B is 129. So this is minus 1 by 12 into here minus 7 minus 29 minus 36, then minus 5 plus 29, 24. So when we divide each of these term by minus 12, we get it as 3 and minus 2. So x is nothing but the variables x and y. This implies x is equal to 3 and y equal to minus 2. Next question. 5x minus 4y equal to 9, 3x plus 7y equal to minus 4. So the given system of equations can be written in the matrix form as Ax equal to B, where A equal to 5 minus 4, 3, 7, x is x and y, and B is the constant matrix 9 and minus 4. So first let us find determinant of A. It is 35 plus 12, which is 47, not equal to 0. Therefore, A inverse exists. And now let us find adjoint of A. It is obtained by interchanging the diagonal elements and changing the sign of the other elements. This is adjoint of A. A inverse is 1 by determinant of A into adjoint of A. So it is 1 by 47 into 7, 4, minus 3, 5. Now Ax equal to B implies x is equal to A inverse into B. So this is equal to 1 by 47 into 7, 4, minus 3, 5 into B is 9 minus 4. So this is 1 by 47 into 63 minus 16, 47, minus 27 minus 20 minus 47. So here we have the variable matrix x and y equal to 1 minus 1. Therefore, x equal to 1, y equal to minus 1. So this is the solution for the given system of equations. Next question, x minus y plus 2z equal to 1, 2y minus 3z equal to 1, 3x minus 2y plus 4z equal to 2. So the given system of equations can be written in the matrix form as Ax equal to b, where A equal to the coefficient matrix 1, minus 1, 2. Here we do not have x term, so it is 0. Coefficient of x is 0, y is 2, z is minus 3, then 3 minus 2, 4. X is x, y, z. And b is 1, 1, 2. So first let us find determinant of A. Expanding along C1. Since there is a 0 there, expanding along C1. It will be easy. So 1 into, here 8 minus 6 is 2, minus 0, plus 3 into 3 minus 4. So this is 2 minus 3, which is equal to minus 1, not equal to 0. So determinant of A equal to minus 1, not equal to 0, implies A inverse exists. Now let us find adjoint of A. Adjoint of A is the transpose of the cofactor matrix. So here we have 8 minus 6, 2, and then here we have a negative sign, 0, minus of minus 9 plus 9. So here it is 9, and then here we have 0 minus 6, and next we have minus 4 plus 4, 0. Next we have 4 minus 6 minus 2, and next we have a negative sign, minus 2 plus 3, 1. And then we have 3 minus 4 minus 1. Here there is a negative sign. It is minus 3, and then 2. The whole transpose. So this is equal to, first row becomes the first column, second row the second column, and third row the third column. So this is adjoint of A. Now A inverse equal to 1 by determinant of A into adjoint of A. So this is equal to, determinant of A is minus 1. So it is minus 1 into 2, 0, minus 1, minus 9, minus 2, 3, minus 6, minus 1, 2. This is A inverse. Now Ax equal to B implies x equal to A inverse into B. So we have x as A inverse is minus of this matrix. So let us multiply with the negative sign. So minus 2, 0, 1, 9, 2, minus 3, 6, 1, minus 2. Into B is 1, 1, 2. So this, when we multiply minus 2 plus 2, 0, and then we have 9 plus 2, 11, minus 6, 5, and next we have 6 plus 1, 7, minus 4, 3. So this is the variable matrix x, y, z. Therefore, x equal to 0, y equal to 5, and z equal to 3. So questions on finding the solution of system of equations using matrix method can be expected for 5 marks. Finding A inverse carries 2 marks. The remaining steps and the final answer carries 3 marks. Next question, 2x minus 3y plus 5z equal to 1, 3x plus 2y minus 4z equal to minus 5. Then x plus y minus 2z equal to minus 3. So the given system of equations can be written in the matrix form as Ax equal to b, where A equal to 2 minus 3, 5, 3, 2 minus 4, 1, 1 minus 2. X is x, y, z. B is 1 minus 5 minus 3. First, let us find determinant of A. Determinant of A, expanding along R1. So it is 2 into minus 4 plus 4, 0, plus 3 into minus 6 plus 4 minus 2, plus 5 into 3 minus 2, 1. So this is minus 6 plus 5, which is minus 1, not equal to 0. Therefore, A inverse exists. Now let us find adjoint of A. Adjoint of A is the transpose of the cofactor matrix. So the first element is minus 4 plus 4, 0, and next we have minus of minus 6 plus 4 minus 2, and then we have 3 minus 2, 1. And next it is 6 minus 5, 1 with a negative sign. Here minus 4 minus 5 minus 9. And next we have 2 plus 3, 5 with a negative sign. Next it is 12 minus 10, 2. Then we have minus 8, minus 15, minus 23. And finally 4 plus 9, 13. The whole transpose. So first row becomes the first column, second row the second column, and third row the third column. A inverse equal to 1 by determinant of A into adjoint of A. So it is minus 1 by 1 into adjoint of A is 0, minus 1, 2, 2 minus 9, 23, 1 minus 5, 13. Now Ax equal to B implies x equal to A inverse into B. So we already found A inverse. It is minus of 0, minus 1, 2, 2 minus 9, 23, then 1 minus 5, 13 into B is 1 minus 5 minus 3. So this is equal to minus of 0 plus 5 minus 6, and next it is 2 plus 45 minus 69, and then it is 1 plus 25 minus 39. So this is 5 minus 6 is minus 1, minus of minus 1 plus 1, and here it is 47 minus 69, it is minus 22, there is one negative sign outside, it is plus 22, then 26 minus 39 minus 13 plus 13. Therefore, x equal to 1, y equal to 22, and z is equal to 13. So this is the solution for this given system of equations. Moving on, solve the following system of equation using Cramer's rule. First subdivision, 2x minus 3y equal to minus 4, 3x plus 5y equal to 13. So in Cramer's rule, we find delta, which is the determinant of the coefficient matrix. Then we find delta x, which is the determinant of the matrix obtained by replacing coefficient of x with the constant. And then we find delta y, which is the determinant of the matrix obtained by replacing the coefficient of y terms with the constant in the coefficient matrix. Then we find x as delta x by delta and y as delta y by delta. So here the given system of equations can be written in the matrix form as Ax equal to B, where A equal to 2 minus 3, 3, 5, x is x and y, and B is minus 4, 13. Now delta is determinant of 2 minus 3, 3, 5. So this is 10 plus 9, 19. Then delta x is determinant of minus 4, 13, minus 3, 5. We are replacing the first column with the constants. So it is minus 20 plus 39, which is 19. Then delta y is 2, 3, replacing the coefficients of y with the constants, minus 4, 13. So this is 26 plus 12, which is 38. So now using x as delta x by delta and y as delta y by delta, here since this delta is not equal to 0, the given system of equations is consistent and has a unique solution. So we have x as delta x by delta, so it is 19 by 19 equal to 1, and y as delta y by delta equal to 38 by 19 equal to 2. Therefore x equal to 1 and y equal to 2. So this is the solution for the given system of equations. Next question, x plus y equal to 1, 5x minus 7y equal to 29. So the given system of equations can be written in the matrix form as Ax equal to B, where A equal to 1, 1, 5, minus 7, x is xy, and B is 129. Delta is determinant of 1, 1, 5, minus 7. So this is minus 7 minus 5, which is minus 12. Then delta x is 129, 1 minus 7. This determinant, it is minus 7 minus 29, which is minus 36. And delta y is determinant of 1, 5, 129. So this is 29 minus 5, which is 24. So we have x as delta x by delta equal to 36 by minus 12, which is minus 3. Then y as delta y by delta, which is 24. This is minus 36 by minus 12, so it is plus 3. Y is delta y by delta, it is 24 by minus 12. This is minus 2. Therefore, x is equal to 3 and y equal to minus 2. Next question, 5x minus 4y equal to 9, 3x plus 7y equal to minus 4. The given system of equations can be written in the matrix form as Ax equal to B, where A equal to 5 minus 4, 3, 7, x is x and y, and B is 9 minus 4. Now delta is determinant of 5 minus 4, 3, 7. So this is 35 plus 12, it is 47. Then delta x is determinant of 9 minus 4 minus 4, 7. So this is 63 minus 16, it is 47. Then delta y is determinant of 5, 3, 9, minus 4. So this is minus 20 minus 27, which is minus 47. So x is delta x by delta, it is 47 by 47 equal to 1. Y is delta y by delta, it is 47 by minus 47 equal to minus 1. Therefore, x is 1 and y is minus 1. Moving on. Next question. X minus 3y equal to 4, 3x minus 9y equal to 12. So the given system of equations can be written in the matrix form as Ax equal to B, where A equal to 1 minus 3, 3 minus 9. X is xy and B is 4, 12. Now delta is determinant of 1 minus 3, 3 minus 9. So this is minus 9 plus 9. This is equal to 0. Now since this is equal to 0, we will not get a unique solution. Delta x is determinant of 4, 12 minus 3 minus 9. So this is minus 36 plus 36 equal to 0. And delta y is determinant of 1, 3, 4, 12. So this is again 12 minus 12 equal to 0. So here delta equal to 0, delta x equal to 0 and delta y equal to 0. So if all these are 0, then the given system of equations is dependable consistent and it has infinitely many solutions. So this system has infinitely many solutions. Moving on. Next question, minus 2x plus y equal to 3, 4x minus 2y equal to 5. So here the given system of equations can be written in the matrix form as Ax equal to B, where A equal to minus 2, 1, 4, minus 2, x is x and y, and B is 3, 5. Now delta is determinant of minus 2, 1, 4, minus 2. This is 4 minus 4 equal to 0. So again we are having a problem since we got this as equal to 0. Now this is determinant of 3, 5, 1, minus 2. This will be minus 6, minus 5, minus 11. This is not equal to 0. So now itself it is decided that the given system of equations is inconsistent and it has no solution. Delta y will be minus 2, 4, 3, 5. So this is minus 10, minus 12. It is minus 22, which is not equal to 0. So here delta equal to 0 and delta x not equal to 0 and delta y not equal to 0. So the given system of equations is inconsistent and it has no solution. Moving on, next question. X minus y plus 2z equal to 1, 2y minus 3z equal to 1, 3x minus 2y plus 4z equal to 2. Same question we have solved in matrix method also. Now we have to solve this using Cramer's rule. So the given system of equations can be written in the matrix form as Ax equal to B, where A equal to 1 minus 1, 2, 0, 2 minus 3, 3 minus 2, 4. X is the variable matrix X, Y, Z and B is the constant 1, 1, 2. So delta is determinant of 1 minus 1, 2, 0, 2 minus 3, 3 minus 2, 4. Let us expand along C1. So it is 1 into 8 minus 6 is 2 minus 0 plus 3 into 3 minus 4 is minus 1. So it is 2 minus 3 minus 1. This is not equal to 0. Next we have delta x. Delta x is determinant of first column alone. We have to replace it with the constants. The other columns will remain the same. So here expanding along R1. So it is 1 minus 8. It is 1 into 8 minus 6 2, then plus 1. 1 into 4 plus 6 10, then plus 2 into minus 2 minus 4 minus 6. So this is 12 minus 12, which is 0. Next we have delta y. Delta y equal to determinant of first column will remain the same, second column will be 1 1 2, third column 2 minus 3 4. So let us expand along C1. Since there is a 0 there, delta y equal to 1 into 4 plus 6 10 minus 0 plus 3 into minus 3 minus 2 minus 5. So this is 10 minus 15, which is minus 5. Delta z is 1 0 3 minus 1 2 minus 2 1 1 2. This determinant. Again let us expand along C1. So it is 1 into 4 plus 2 6 minus 0 plus 3 into minus 1 minus 2 minus 3. So this is 6 minus 9, which is minus 3. Now x will be delta x by delta. So it is 0 by minus 1 0. Y is delta y by delta. It is minus 5 by minus 1 5. Z is delta z by delta. It is minus 3 by minus 1, which is 3. Therefore, x is 0, y is 5 and z is 3. So this is the solution for this given system of equations. Next we have the next question, 2x minus 3y plus 5z equal to 1, 3x plus 2y minus 4z equal to minus 5 and x plus y minus 2z equal to minus 3. Here if we had this equal to 11, we will get the answer given in the book. So the answer which we get here will be different. So the given system of equations can be written in the matrix form as Ax equal to B, where A equal to 2 minus 3 5, 3 2 minus 4 1 1 minus 2. X is x y z and B is 1 minus 5 minus 3. So now let us find delta. Delta is determinant of 2 minus 3 5, 3 2 minus 4 1 1 minus 2. Same question we have done in matrix method also. So here let us expand along R1 equal to expanding along R1. 2 into minus 4 plus 4 0 plus 3 into minus 6 plus 4 minus 2 plus 5 into 3 minus 2 1. So this is minus 6 plus 5 equal to minus 1. This is not equal to 0. So we will have a unique solution. Now delta x is the first column becomes 1 minus 5, 3. Minus 3, 2, 1, 5 minus 4, minus 2. Here again expanding along R1. It is 1 into minus 4 plus 4, 0. Then plus 3 into, it is 10 minus 12 minus 2. Plus 5 into minus 5 plus 6, 1. So this is minus 6 plus 5, which is minus 1. Next we have delta y. Delta y is 2, 3, 1. 1 minus 5 minus 3. 5 minus 4 minus 2. So this is 2 into, here we have 10 minus 12 minus 2, minus 1 into minus 6 plus 4 minus 2, plus 5 into minus 9 plus 5 minus 4. So this is minus 4 plus 2 minus 20. So it is minus 24 plus 2 minus 22. So delta y is minus 22. Next we have delta z. Delta z, it is 2, 3, 1, minus 3, 2, 1, 1 minus 5 minus 3. Again expanding along R1. It is 2 into, here it is minus 6 plus 5 minus 1, plus 3 into minus 9 plus 5 minus 4, plus 1 into 3 minus 2, 1. So this is minus 2 minus, it is minus 2 minus 12. So it is plus 1 minus 13. So delta z is minus 13. Now x is equal to delta x by delta. So it is minus 1 by minus 1, 1. Then y is delta y by delta. It is minus 22 by minus 1, which is 22. And z is delta z by delta. It is minus 13 by minus 1, which is 13. Therefore, we get x as 1, y as 22, and z as 13. So this is the solution for the given system of equations. Next question, x plus y plus z equal to 0, minus 3x plus y minus 4z equal to 0, and next we have minus 2x plus 2y minus 3z equal to 0. So here we can see that all these are equal to 0. So this system is a homogeneous system of equations. Now let us see what kind of solution we will get. So the given system of equations can be written in the matrix form as Ax equal to b, where A equal to 1, 1, 1, minus 3, 1, minus 4, minus 2, 2, minus 3. Then x is equal to x, y, z, and b is equal to 0. First let us find delta. Delta is determinant of the coefficient matrix. Expanding along R1. So this is 1 into, here it is minus 3 plus 8, 5, minus 1 into 9 minus 8, 1, plus 1 into minus 6 plus 2, minus 4. So it is 5 minus 5, which is 0. So we have delta as 0, and we will have delta x as, this first column will be 0. So delta x will be 0. Then delta y, if we find second column, we have to substitute 0. So delta y will also be equal to 0. And delta z, we have to substitute third column as 0. So delta z will also be equal to 0. So we have infinitely many solutions. So delta x is equal to 0. Then delta y is 1 minus 3 minus 2, 0, 0, 0, 1 minus 4 minus 3. If any one row or column in a determinant is 0, then the value of the determinant is equal to 0. Delta z is 1 minus 3 minus 2, 1, 1, 2, 0, 0, 0. So this is also equal to 0. Therefore, we got delta equal to 0, delta x equal to 0, delta y equal to 0, and delta z equal to 0. So, the given system of equations is dependable consistent and it has infinitely many solutions. So, this is the answer for this question. And next we have the last question. 2x minus y minus 3z equal to 1, 3x plus 2y minus 5z equal to 0, 5x plus y minus 8z equal to 3. So the given system of equations can be written in the matrix form as Ax equal to b, where A equal to 2 minus 1 minus 3, 3, 2 minus 5, 5, 1 minus 8. X is x, y, z. And b is 1, 0, 3. Now delta is 2 minus 1 minus 3, 3, 2 minus 5, 5, 1 minus 8. So here let us expand along R1. It is 2 into minus 16 plus 5 minus 11 plus 1 into minus 24 plus 25, 1 minus 3 into 3 minus 10 minus 7. So this is minus 22 plus 1 minus 21 plus 21, which is 0. So we got delta as 0. Now we do not know what we are going to get for delta x and delta y. Delta x is first column becomes 103, the other columns remain the same. So let us expand along C1. This is 1 into minus 16 plus 5 minus 11 minus 0 plus 3 into 5 plus 6 is 11. So 33 minus 11, 22. So we got delta as 0 and delta x is non-zero. So here itself we can conclude that the given system of equations is inconsistent and it has no solution. Let us find delta y and delta z also. 2, 3, 5, 1, 0, 3, minus 3, minus 5, minus 8. So this, when we expand along R1, it is 2 into 15 minus 1 into 1 minus 3 into 9. So it is 30 minus 28, 2. Again delta y is also not equal to 0. Delta z is 2, 3, 5 minus 1, 2, 1, 1, 0, 3. So let us, this is expanding along R1. Here let us expand along C3. It is 1 into 3 minus 10 minus 7 minus 0 plus 3 into 4 plus 3, 7. So it is 21 minus 7, 14. So this implies delta equal to 0, delta x, delta y, delta z are non-zero. So we get the given system of equations is inconsistent and it has no solution. So these are the solutions for the exercises from the second chapter algebra, that is matrices and determinants. I hope this video was useful for you. If you have not subscribed to my channel, please subscribe. If you find this video useful, share it with your friends. Thank you for watching.